This video is brought to you by mywayteaching.com.
Okay, next topic is equilibrium in chemical processes. Dynamic equilibrium. Okay, so dynamic equilibrium, it consists of a forward reaction in which the reactant gives product and reverse reaction in which the product gives the original reactant. It is analogous to the physical systems. Chemical reactions also attain a state of equilibrium. Okay, so dynamic equilibrium which gives a forward reaction, which gives a forward reaction, that is from reactants to products. Okay, so and also there is a reverse reaction from this is reactants to products. It gives the products to always the reactants this side and this is product. So in the reverse direction, what happens? The arrow should be, this is the reverse reaction. Okay, which gives products the original reactants. For better comparison, let us now just consider the general case, reversible reaction. So you just consider the general equation, a plus b to c plus d. Okay, so with the passage of time, there is the accumulation of the products C and D and depletion of the reactants A and B. This leads to a decrease in the rate of forward reaction and an increase in the rate of reverse reaction. So this is A plus. This is attainment of chemical equilibrium. C, which I have written A plus B, C plus D. Okay, so what happens in the forward reaction? There is accumulation of the product C and D and depletion of the reactant C. The product increases and depletion of the A and B. Okay, so where they attain both, this is the equilibrium state. Okay, eventually the two reactions occurs at the same rate and the system reaches at a state of equilibrium. This is attainment of chemical equilibrium. Next, this is the depiction of equilibrium for the reaction. As shown in this figure, this is the molar concentration versus time. Okay, so this is the depiction of equilibrium for the reaction. In this, what happens actually? See, I will write N2 plus 3H2 2NH3. Okay, so N2H2NH3 and then come to the dynamic nature of chemical equilibrium can be demonstrated in this synthesis of ammonia by Haber processes. In a series of experiments, Haber started with known amount of dinitrogen. Okay, see here, this is the dinitrogen. And dihydrogen maintained at high temperature and pressure and at high regular intervals determine the amount of ammonia present. Dihydrogen, see, this is dihydrogen, reactant dinitrogen and ammonia is the product. What happens? Dinitrogen, dihydrogen and ammonia is the product. He was successful in determining also the concentration of unreacted dihydrogen and dinitrogen. Shows that after a certain time, the composition of the mixture remains the same even though some of the reactants are still present. This constancy in composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting conditions but using dinitrogen or deuterium in place of H2. The reaction mixture starting either with dinitrogen or dihydrogen reach equilibrium with the same composition, except that dihydrogen and ND3 are present instead of H2 and NH3. After equilibrium is attained, these two mixtures are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of ammonia is just the same as before. So, if you are observing in this ammonia, so it is same as the before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all deuterium containing forms of ammonia and dinitrogen and his deuterated forms are present. Okay, so use of isotopes in the formation of ammonia clearly indicates the chemical reactions reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in the composition. Okay, so this is the use of isotopes in the formation of ammonia. It clearly indicates that, once again I will repeat, chemical reactions reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in the composition. Okay, similarly, let us consider the reaction dihydrogen plus iodine, which gives HI. Okay, if we start with equal initial concentration of that is H2 and I2, the reaction proceeds in the forward direction and the concentration of H2 and I2 decreases while that of HI increases, so that H2 and I2 decreases when the HI increases. Okay. Mm, until all these become constant at equilibrium as shown in this figure. So here H2 I2 decreases, HI increases at some value they attain equilibrium condition. Okay, we can also start with HI alone and make the reaction to proceed in the reverse direction. The concentration of HI will decrease and concentration of H2 and I2 will increase until they all become constant when equilibrium is reached. If total number of H and I atoms are same in a given volume, the same equilibrium mixture is obtained whether we start it from pure reactants or pure products. So this is the figure chemical equilibrium in the reaction H2 plus I2, which gives the 2HI in the gaseous state can be attained from either direction. Okay, so this is about the what happens. So when this is one example where H2I2 decreases, HI increases, so means reactants decreases, which gives a products. When both are decreases, so which increases in the HI, then hydrogen iodide. So this is the example. Next, where this is the figure that is expression involving the equilibrium concentration of the reactants. Okay, expression involving equilibrium concentration of the reaction. Then is law of chemical equilibrium and equilibrium constant. Okay, first let us consider a general reversible reaction. You know, general reversible reaction. What is reaction? A plus B, C plus D, where A and B are the reactants and C and D are the products in the balanced chemical equation. On the basis of experimental studies of many reversible reactions, the Norwegian chemist Cacho, Maximilian Guldberg and Peter Wag proposed in 1864 that the concentration in an equilibrium mixture are related by the following equilibrium equation. Equilibrium equation, that is Kc is equal to C D A B. Okay, where Kc is the equilibrium constant Kc is equal to, and the expression on the right side is called equilibrium constant expression. The equilibrium equation is also known as law of mass action. The equilibrium equation is also known as the law of mass action, because in the early day of chemistry concentration was called active mass. In order to appreciate their work later, let us consider the reaction between gaseous H2 and I2 carried out in a sealed vessel at 731 Kelvin. Okay, that is H2. Okay, this is 1 mole, 1 mole, 2 mole. At a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. This is known as the equilibrium law or law of chemical equilibrium. Okay, what do you mean by law of chemical equilibrium? Please note down. At a given temperature, the product of concentration of the reaction products raised to the respective stoichiometric coefficients in the balanced chemical equation divided by the product of concentration of the reactants raised to their individual stoichiometric coefficients has a constant value. This is known as the equilibrium law or law of chemical equilibrium. Okay, next, you know that the equilibrium constant for a this is one equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. The equilibrium constant for a general reaction, I will write equilibrium constant for a general reaction. BB CC plus DD. So these are the equilibrium what coefficients. Now you can write equilibrium constant okay. So A, B, C and D are the equilibrium concentration of the reactants and the products. So next is the equilibrium constant for the reverse reaction here, which is inverse of the equilibrium constant of the reaction in the forward reaction. Okay, that is how you can write off this one. Kc is equal to 1 by Kc. Okay, next, relations between the equilibrium constant for a general reaction and its multiplies. I will write this is chemical equation equilibrium constant. That first one. Kc N. Okay, so this is the relationships between equilibrium constants for a general reaction and its multiplies. Please note it down. This is Kc. Okay.